There.
I mean, it's sort of like the you know, the RAID array of floppy drives I saw one time. But
Yeah, well, you know, there's when you look at the cost point and what you need to do, there are valid reasons to do a lot of things.
yeah,
And sometimes just because it's the coolest hack ever
Right.
is a perfectly valid reason, right? I told you I've got a friend who writes Minecraft servers that'll go on an
Right.
Uno, right? So they don't do much, but
yeah. So here's a floppy disk RAID array because they could. Yeah, no, it's. I know. I'm being careful. As careful as I care to with this old piece of crap.
I've had to replace way too many
Yeah.
power ports, and it's never fun.
No. No. This has been a little wiggly for a while. For the most part, I'm good to it.
my machine's in super slow mode for some reason.
You hit the turbo button.
It's trying to update
The
it.
turbo button. It won't, and I'm trying to tell it to open up File Explorer and it won't. Oh, there we go. Oh, now 40 of them open. There we go.
Why did this order 40 of this test? Because you put a 40 in this box.
That's what I tell my kids and complete noobs. Quit clickety click click clicking.
Yep.
Give it a chance.
Be patient.
Let it catch up. It's
I don't
clearly
want to be patient.
clearly busy. I'm gonna open up. I've got a little class order. What comes next? What comes next? What comes next? So, all right. I guess we can get started. It's 7:30 almost. Looks like everybody that's going to be here is here. We got a big crowd tonight, so that's cool. Got 2 new gluttons for punishment, and they probably won't be here again ever.
If you'd stop scaring them away.
Yeah, well, you know, try to be
I have
honest.
a card with numbers, and I'm going to rate you the entire time and just hold the card.
Does it have negative numbers in front? Do you have negative
I'm
numbers?
just kidding now. Thanks for putting this on.
No, it's dry. I get it. It's dry.
Yeah.
It's a lot of dry material, and you know, I'm not offended if you don't come back. I'm in fact kind of impressed if you do. Damn, you are tough. So, what was it last time? I'll take these. These are like exactly wrong for anything that's the distance I like to work. So, last time we talked about SPI, Serial Peripheral Interface. Just, whoops, so you can see it spelled out. And the way SPI works, we talked about serial protocols, how you send data up and down. SPI is a 3-wire. On your master, you have a master and you have a slave. Master tells people what to do, slave does what he's told. So when you do this, you write a piece of software for this one, and if you've got 2 Unos, you'll write a piece of software for that one, and they'll understand how to talk to each other. And you have Mosey, which means master out, slave in. So if you're the master, that's your output. And it comes over here to meso, master in, slave out. And he sends data back off of his Mosey to this guy's meso. So Mosey to meso, Mosey to meso, and then you have clock. And master controls the clock. That means that everybody's synced to master. So now you look at this and you say, well, that's easy. You put a register here and a register here, and if I want to load something, I put it in there, and if I want to read something back, I put it there. What SPI's done is they've gotten clever, and they've got one 8-bit register that does that. And the clock source in here not only goes out, but I guess the right way to draw this is something like that with an edge on it. Same thing on the other end, you set them up the same and they talk. So you put 8 bits in, you shift it out. At the same time that you're shifting it in, you shift it out, it comes into this guy and that bit comes right back out down the line. So when you shift a bit that way, you get a bit this way. So when you do everything right, you say, hey, you do this command, now I want to read data back, and that data is coming back. And so you can say, you do this, and then you can say, you do this other thing, right? You can pack bits. You, and we'll get into why you, do this, and then you can do you, do this. And so this is all going this way. At the same time, you do this. When I'm sending you, I get result. Whatever. Result. Whatever. So I can send a command at the same time. So I've just made it not super, it's asynchronous. It's not asynchronous. It's full duplex. I send something and receive something at the same time. I could do a whole string of things. If I say do this and what I'm expecting is 20 bytes back, but then this next one's supposed to do something else and not send me a byte back, I can do that and just keep running and keep getting my 20 bytes. Well, that thing goes off and turns on a light.
And just for clarity, the clock is what makes sure that they're all speaking at the same
Clock.
speed.
Clock stays at the same speed.
Yeah. Just keeps them synchronized.
Right, so if you're looking at RS-232, Ethernet, RS-422, RS-485, several of these other serial protocols that we're familiar with, the way your modems work. If I tell this computer to talk to that computer over an RS-232, they are two completely separate clock domains. He might have a 3 gigahertz clock, he might have a 2 gigahertz clock. You get down into the transmission and receiving hardware, you'll have a clock, you'll agree on your baud rate, 9600 baud, your data formatting 8-in-1, which would be 8 bits, no parity bits, 1 stop bit, and you'll start to talk. And the longest, I think you can send 12 bits, and as long as you stay within the timing constraints, you're guaranteed that those two clocks won't walk off of each other.
Yeah, because
In that 12 bits.
if they start doing that, then the you do this, it might read the you part as the do this part. It gets out of sync. So
Right, so
it's very
so, yeah.
specific on
This
where,
this guy has a clock that's going this fast, and this guy has a clock that's going that fast, right? And now I say I want the rising edge to be when I capture the data. And so I put data like this on that guy, so I'm expecting you to capture the data here. But what happens is, pull out some green, and this is a single bit, so I get that, I get that, I get that. I don't know what I got.
yeah, the
I
data
don't know if I
stream,
got this, I got that, you know.
the data stream's kind of a fire hose, and you just got to know when to read it and
It's all
what that
timing.
means. Yeah.
So, and we're gonna do an exercise tonight. That's gonna be the lights out and us making noises. So
Oh boy.
it's not as dirty as it sounds. Darn it. Okay, so now here's the deal. This is the simplified version of this. The SPI standard's loose. So, you know, it says, okay, 8 bits in, 8 bits out. You've got certain clock rates that you're allowed to do, And maybe you can go as fast as you want, but here's some standard clock rates. You can change things. You can say that, you can change clocking. You can say, instead of data going out on the changing on the falling edge, right? So if I time is that way on an axis. So I'm moving, that means this happens first and then that happens. So this is a rising edge, that's a falling edge, rising edge, falling edge. On a clock, it's a periodic, tick tock, tick tock, tick tock, tick tock, tick tock. So I can say, there's setup registers in here that you can program this, and you say, I want my data to go out on the rising edge, and what that means is all this data shifts a half a bit time-wise, because now it'll be going out on the rising edge, right? So what you see here is, this is a falling edge, and I'm changing my bit on the falling edge. So I'm putting my data out on the falling edge so that it's guaranteed to be valid on the rising edge. It's all timing considerations, trying to get your timing right. But I can say, you know, this guy on the other end, he can only read falling edges, so he needs to read on a falling edge, so I need to put it out on a rising edge. That shifts all this way, but now your timing's good for the guy who's receiving it. You can also play the game that, oh, he receives and sends the same way I do, but my wire's 3 miles long, for whatever reason, and it's going to phase shift. You know, I'm going to send the clocks, but for some reason that wire's longer and it takes longer to get there. I can say I'm sending it out on a rising edge, and you receive it on a rising edge. So and there's four combinations. There's send, receive. You can do this. You can do that. You can do that, and you can do that. This is the most common one. That's mode 0, I think. There's some other things. You can actually diddle the phase just a little bit, stuff like that. But it's a loose spec, and nobody says, there's no universal spec that, the spec is just, this is the core functionality you got to be able to do. Beyond that, play with it however you want. So, that said, I was telling you last week, 2 weeks ago, last class, that I was going to show a demonstration of an I/O expander. So let's talk about what's an I/O expander. I don't remember if we talked about this last week or not. I think we did. So I've got my Uno here, and he's got 13 digital bits, I think, like 0 through 13, and then there's 5 analog. So these are GPIO. That would be 0 to 12. These are GPIO, general purpose input output, and these are analog or GPIO on an Uno. And this is 0 to 5 or 4?
It says 5.
5.
Were the ones with the tilde analog or those PWM? I forget. The pins with the little, it looks like a hyphen on it, but I think it's supposed to be a tilde.
It's a tilde. So those are not, those are analog outputs. The PW, those are things that, remember we did the drawings of how the PWM software works, and we did that. Those pins can do PWM.
Okay.
They tie directly to output hardware inside the AVR microcontroller
Right.
that can do PWM. And so you can't exactly do analog, but you can do things that kind of look a lot like analog. And if you put the right kind of filters on the back end of it, it sounds like bad audio.
But the analog ones, I guess, are marked with an A then, right? I think there are some pins marked with an A.
Okay, so these are analog inputs.
Okay.
Analog in or GPIO. Now you can switch them. You can make them run as GPIO.
Right.
Or they can be analog. So what that said, and so this one's like This one's TX and RX for RS-232. So you say, you know, if I want to communicate back to something, I need those two lines. If I've got some number, if I've got 6 analogs in, right, now I'm down to 10 lines left, or actually 11 lines left. And I've got, you know, a push button here and whatever, you know, whatever else is going on. If I'm using the SPI to drive something, okay, well, let's not talk about SPI. I2C to drive, that might be a bad example. I2C and SPI might be on the same pins. But you can see it's not hard to imagine that you could rapidly use things up, right? If I've got 4 LEDs there, now I'm running down and I say, well, shoot, I need 8 more I/O. Well, I don't have 8 I/O there. So what an I/O expander lets you do is they make them in I2C and they make them in SPI and they probably make them in other formats, I don't know what, but you can use Meso, Mosey, clock, and chip select. And you can come out here to the I/O expander.
And the Raspberry Pi has GPIO as well, so a lot of this is applicable to that.
Yeah, but the Raspberry's got like 32 or 64 I/O. It's got a lot more.
Yeah.
So now instead of going up to a Arduino Duo or an Arduino Mega and paying $40 for it or $35 for it, or going up to a Raspberry Pi and paying certainly $35 or $40 for it, I bought 2 of these and they were about $50 each. So at a, you know, you get price breaks usually at 5 or 10 and then 20 or 50. And so what this does is I've got Meso, Mosey, clock, chip select, and then I've got A0, A1, so what I bought are the exact same chips, I think. I bought 4 chips, 2 of them are SPI and 2 of them are I2C. They're exactly the same inside. They're both made by Microchip. The only difference is whether it's an SPI or an I2C interface. SPI on these has these 2 bits, and so this is SPI, and this is I2C. So those 3, I think. And then you got power or ground, power 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's an interrupt line. 9. There we go. 1, 2, 3, 4, 5, 6, 7, 8. 18 pins. So I take these 4 lines. Now these are address lines. So if I tie them all low, then that device has address 0. And it follows binary, with A0 being the least significant bit. So it can be, if I say that, I don't know if I can do this, fingers out are highs. So that's address 0, 1, 2, 3, 4, 5, 6, 7. Right, so I can have 8 devices sitting out here, and if I were to do that, then I would have another one right here like this, tied up, tied down, Meso, Mosey, clock, chip select, but he would have his own set of addresses, so this might be address 0 and this might be address 1. Now for $3, I just went to 16 I/O. For $6, I can go to 32 I/O, right? It doesn't cost me much to gain a lot of I/O. Drawback is, you know, here, if I change a bit on this pin, I know it right away. I can sit there and do nothing but look at that pin it changed. Right? You know, do something. Turn on an LED. Oh, it changed. Turn that LED off, right? That was like our very first, right? We push a button and watch the light turn on and off. That was hello world, I'm doing something and it's doing something in response. Now, when I first start up, I've got to go set these guys up. They've got, in this particular instance, they've got 1, 2, 3, they have 10 different registers inside of them. And one register is like, I want to set this up to be a 1 is an input, a 0 is an output. Nice, because it looks like an I and an O. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Aha, see, it's off by a bit. Output, 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 output. If you're not using a pin, generally speaking, make it an input. Because if you make it an input, it's high impedance and you don't have to worry about shorting something. Because if it's high, it's got 5 volts on it, just waiting to touch something and make a spark. And if it's low, it's just sitting there waiting as a ground, waiting for something to come in that's got some voltage on it to make a spark. So if you're not using them, make them an input. They go high impedance, current don't conduct. Not enough to be noticeable anyway.
By the way, for reference, I've heard that the hardware version of Hello World is getting too blinky. Making something blink. So.
Well, so the first Hello World is to make a light blink.
Yeah.
The problem with the Arduino Uno is it ships with Blinky on it.
Yeah.
So when you sit down and you write your code and push blink out, you don't really know if you pushed a blink or not.
Right.
Right? Because it's already blinking, and if it's the first time you've ever done it, you probably went out and grabbed their example code, took a look at it and said, I understand what that does, pushed it on there and said, well hell, it does exactly the same thing. I don't know if I did anything or not. So yeah. When you're at bare metal,
Yeah.
that's the first.
That was more the intent of it, was going from knowing nothing to getting a light to blink. That's the Hello World version of hardware.
Yeah, it is. It really is. Everything I've done that's new hardware, that is the first thing I do.
Good test.
Can I make a light blink? Because on these, like I said before, the IDE hides a lot from you.
Yeah.
It makes it pretty easy. Remember when I did the interrupt code and all that assembly code I was showing on the sides, how I turned on the interrupts and did all the stuff? For every I/O port, you got to do that. For every different little function you want to do, I got to do that. When you use their built-in libraries, they do a bunch of stuff behind the scenes. You know what it's doing, but in the end it did what I wanted it to do, right? So that takes that onus off of you to have to learn that. The flip side is, as I've shown you, it's not real efficient. If you really want to get up and make it do a little tap dance and do some things that are timing critical, you're going down into assembly code. Or at least C code. Because C code is only like, a quarter of a step away from assembly. So now on this thing, this particular, like I said, the standard is loose. So as long as you follow the base, what they say the hardware has to do, you can make these things work any way you want. So these particular chips, they have these address bits, and they have the chip select. If chip select is high, it ignores everything. So there's actually 2 ways you could do this, right? If I had 14 chips, I could run 14 chip selects out. And one Mosey Mesa, and have all of them be at address 0. And then I could say, oh, well, everybody's address 0, that makes that simple, and I just tie this line, that line, that line, that line, that. I want to talk to you. And originally I thought I wasn't even going to use chip select, I was just going to leave it always selected, and I would just talk to it and make it do what it was going to do. And then I read the data sheet, and this particular chip select, going from a high to a low, that's its signal to listen. So if you tied it low so it was always selected, because I thought, you know, it's got an address, I'll just send addresses out and it'll only listen to the one that's for it. Chip select is how it knows on this stream of clocks that it should have started listening. I use the Arduino built in. If you look, if you've got the IDE up, if you go to Sketch, you'll get 4 options in a drop down. The bottom one's Import Library. If you go over to that, you see a whole list of libraries down the side, and down about the end of the S's is SPI. So the way their SPI library works is chip select goes low, clock then starts, and then stops. And then data comes out, right? Those could be 1 or 0s anywhere along the line. Their library uses an interrupt that is also used, I think, for RS-232 and something else, I don't remember what. So they have a function that's called begin transaction and ends transaction. If the only thing this thing is ever going to do is talk to these guys, and you're never going to rely on a timer, I don't know that you actually got to worry about the timers, but you're never going to rely on serial to talk back and forth, debug, or something like that, then you can just begin the transaction in your setup code and never end it. I wrote my code to be friendly, so when I say I want to write a bit, it goes out, it opens a transaction, it writes the word, then it closes the transaction. And so I have a write and a read that do both. What you send for these guys is a 0, 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8 bits. So that's the address, and I can't remember for the life of me. I think it's A0 and A1. I don't remember. And then it's a command. Or actually, it's not a command, it's an address. And then it's data. And for me to draw this right, I should have this over here like that. And this took me a little bit to figure out because in the data sheets it always shows it here like I drew it originally. I was like, well, what do I do with the data? How do I... do I need to bring it high and keep clocking? And so I've got an oscilloscope out and I'm looking at all the lines and watching what's going on. And then I found out that this chip is rated at... On I2C, it's rated down really slow, like 120 kilohertz or something like that. You know, it can do this, it can do this, it can do this, and for I2C, it can do 5 megahertz and it can do 10 megahertz. And I made a mistake in the command to initialize the SPI library. I used a byte instead of a long. So 8 bits instead of 32 bits to represent 10 million. And so I don't know.
Not so much.
I don't know what it actually had in the register. It was running really slow. And I didn't catch on that. And I'm sitting there wondering, why in the hell? I've got, because I was sending, hey you, do this. Here's the data. And the data is just 4 bits, which you can see right there, ticking through, counting binary, a version of Hello World. And it wasn't happening. And I'm looking at the protocols, and it's like, well, that's all correct. It's doing what it's supposed to do. I'm reading the data sheet. That's what it's supposed to do. It was too slow. It couldn't do it. It was too slow. Remember I said that you could actually run things too slow? That's one of them. when I said, oh, that should be a long recompile, bang, it worked. Right off the bat. It's running at 5 megahertz, so I'm putting a 5 megahertz data stream out. And if we were sitting here with a AM radio, might be able to hear it. We'd hear. So, the other thing I did, so on this thing, I wired up a switch out here. How did I wire the switch? I think I wired it this way. Like that. And then I wired an LED here. And there's 4 LEDs here. These 4 LEDs actually have resistors in them, have ballasts. That one doesn't on mine because I played around with these before. That particular diode doesn't mind that I don't put a ballast on it. Those ones rapidly turn black if I don't put ballasts on them. They make one little bright boop and then they're done. So there should be a ballast in that one. This is the pull-down resistor. So when the button is not pushed, I see 0 volts. When the button is pushed, 5 volts comes in. I get 5 volts. And the result of that is here. Hopefully people at home can see this. Actually, the button's probably reversed. Yeah, the button's reversed. I got 5 volts on it. But notice it took a second for it to turn off. We understand why that is? It's because I push the button here. This has to tell me, hey, read that data back. Oh, I got it. Now take that bit back out and put it in. So that's the time. What you're seeing there is the time that it takes for this to go all the way in, do the math, turn around, come all the way back out, and put it on the chips. So instead of if this was tied up directly, when I pushed that, it would take microseconds. I mean, bang! You wouldn't be able to tell, looking at it, that it took any time at all. Here,
So
I have to do this data
period
stream.
of time you have to interrupt the switch in order to get a result. It's because once you pressed it, you held it long enough where it didn't happen before you let go of the button, but we saw it. But then a couple times when you tapped it, it wasn't long enough to catch it.
Right? Yeah, I can.
So it's how long till it comes around and reads it actually has to be down long enough for the input to be read.
Yeah.
Yeah.
So you've got the standard digitals. Well, this is GPIO, so there's going to be a setup and hold time for the register that's inside of there.
Is that programmable, or is that because of the expansion across the meat?
That's a combination of me having to go into a library, tell this thing to turn on, come over here, send that data out. Because what I have to do is I have to send the data to read.
To read, yeah, okay.
And what I'm doing is every time I'm doing a write, I'm not being smart and using interrupts on this. I'm doing a write and then a read. A write and then a read. And then a write and then a read. So that's 24 bits. That's 24 bits out, and then when I do the read, it's this. I change that bit right there. A 1, I can't remember. A 1 means write, or a 0 means read, or maybe it's the other way around.
Okay.
Read the data sheets.
Yeah.
So I say write this address, this data. So I say write the output ports, these 8 bits, and there's a register in there that gets those 8 bits. And it will only put the outputs out on those 5, because these other ones are inputs, so they don't see that register. And then I say this address, with a read, this device, read the input register. So all these inputs go in. And in fact, all the outputs get read into that register too. So it reads out exactly what the state is of all of them right there. And then I have to do another 8 bits of clocks. I just send 0, 0, but that gives me the data back into this register over here. Then now I go and I read it and do the right things with it. So 1, 2, 3 times 2 is 6 times 8 is 48. 48 bits at 5 megahertz is around 10 kilohertz. Right? Did I do that right in my head?
I can't verify that, but
It's 5 megahertz clock, so that's 5 million. And I've got, call it 50. 5 million divided by 5 is 1 million. 1 million divided by 10 is 100,000. 100 kilohertz. I said 10 kilohertz. It's 100 kilohertz. So now that's 100 kilohertz, and then on top of that, I've got the overhead in here of turning it on, turning it off, do this, do that, do the other, whatever it is it has to do. Super inefficient code. You can set these things up to do a couple of different kinds of interrupts. You can set it up, so if there's the interrupt pin. I could bring the interrupt here back over to one of the pins that can do interrupt on change. And then this thing, I wouldn't have
if
to
we
read.
change the cycle and immediately send the result of the input, right?
Well, no, what it would do is, there's 2 different ways you can do the interrupts on this thing. One is, you can say, if any pin changes, light the interrupt. So then I would light the interrupt, and I would, instead of doing a right, as soon as I got the interrupt, I'd do this, and I'd have the data back. And then I could do something with it. So that would perhaps speed up some of the different things. The other thing I can do is I can put a bit mask in there. So I can make them all inputs or whatever. And I can say, if this one ever deviates from a 1, make an interrupt. But if this one ever deviates from a 0, make an interrupt happen. So I can tell you, I can put my 4 bits out there like this. I can't do that with that pinky finger. And if I ever get a deviation from that, if this one or that one or that one or this one, you're going to give me an interrupt because I want to know it then. So that lets you grab it pretty much as soon as it happens. At least, if there's anything that's timing critical, you can say, oh, that happened. This is when it happened. Now let's get the stuff in here so I can do something with it. So, you are exchanging a lot of I/O for speed. There's very good reasons to do that in a lot of different things. You can have a really fast little processor that doesn't have much I/O. They make some of these that are 6 pins. It's got Meso, Mosey, clock, power, ground, and 1 bit. But it's got all the same power that 32-bit guy, or that this guy has, this 18 mega has. I mean, you want to conserve space. But over here, I need to get some stuff. There's valid reasons for doing things. So as telling a friend of mine, engineering, when you're designing something, there is not one answer. You have a series of requirements that you want to meet. Depending on which way you come at it from, different things will make different sense. And I have more experience with these, and maybe you've got more experience with pies. And you'll look at it, and the first thing you'll think is, this is a perfect place for a pie. And I'll look at this and say, this is a perfect place for an Uno, or this is a perfect place for an FPGA, or this is a...
When all you have is a hammer.
When everything looks like a nail.
Exactly.
Or actually, everything looks like it needs a dent in it. Yeah. All right. So I have beaten SPI to death. I still have not uploaded my code somewhere where everybody can get to it. So harass me and I'll do that. I actually touched my website here recently. I need to do more to make it more friendly for this kind of thing. my website's very unfriendly because it's all hand coded, directly HTML. So,
You don't just want to put it like in a Google Drive or a Dropbox with links to it?
my Google Drive's almost full.
Well, you just sign up for another account.
Well, and
I pay 10 or 20 bucks a month for a website with some god awful number of gigabytes of storage on it. It's full of pictures. It's full of my truck. It's full of silly projects. So now we're going to talk about Ethernet. Because here's what I think. I think we're moving along, and at some point we're going to want to do something useful with one of these things, or a nice little project to get us to learn stuff. And maybe Ethernet's not what you want to do. I'm going to go through a couple of more things. I've got a list of 1, 2, 3, 4 different things that we can have individual classes on, and then come in and talk about maybe a little group project and say, you know, do it this way, do it that way. I don't care which way you do it, but let's do it. And that gives you, I mean, the best way to learn something is to have a project to focus it on, right? I mean,
definitely have a goal.
I mean, I've been doing data camp for their Python for data analysts thing, and yeah, it's great. There's a lot of things I've learned there. I am not going to remember any of it because I don't. I'll have been exposed to it, so the next time that I need, if I ever actually need to do it, I won't be a complete noob in the woods. But
I try to explain that to my staff all the time. It's like, you know, they're like, I need to learn that. I'm like, no, you don't really need to learn that because you don't use it every day. You're never going to remember it. Understand the general concepts behind it.
Yeah.
And then
Yeah.
Google.
Yeah.
yeah,
Google as needed.
yeah, and Google is your friend.
GAN.
Although today my phone's autocorrect won. I told somebody they needed to Google something, and it said you need to go ogle something. I'm not even going to change that. That's most.
Well, I have a you know, if you contact me and you have not Googled it, you're in trouble.
A lot of that happens a lot at work. It's like, I don't know, what is this? How does this do this? It's like, you're sitting at a computer. Ask Google.
Well, let me Google that for you.
That's what I tell my kids. Wait, I have a stupid question, Dad. You have the internet in your hand.
My wife asked me what the temperature is outside. I'm laying in bed. I have no frickin' clue. We both have phones. Hers is already, you know, on her. Why are you asking me?
Just ask Alexa.
Yeah,
No,
Alexa, Siri, hey Google.
Did I tell you? Does yours have voice? Does yours have sound hooked up out here?
Is she talking out there?
No. She might have.
Does she have sound hooked up?
She's technically connected to the Bluetooth speakers over here if you want more sound than she puts out.
No. I was just asking because the other day I think I broke her. I walked in and said, Alexa, or Hey Google, whatever.
It's
Alexa, would you be my girlfriend? And like the lights went on it.
And then it just turned off.
It was just dead silent.
Yeah.
It's just like,
Wow, man. It had hurt enough of you that knew that it should not
I'm
respond.
like, damn.
So we
Even a chatbot doesn't want to talk to me.
we've had an Echo and a Dot for a while, and we just got a Google Mini, the little puck one. And the other night she said, hey Google, do the thing, and it came back like, oh, okay. Like, but sarcastic.
Have you heard the bit where they got two of them arguing with each other?
Yeah.
I've wanted to do that. I think it was yours. I came in here one day and said, who's better, Siri or Cortana? And it said, I like all AIs equally.
Yeah.
Anyway, off topic.
We put some sass in there.
Find some shiny things to go chase here. All right, Ethernet. Now this is going to be awful because I'm going to go into some history. But we're going to talk about two things. You have an Uno does not have Ethernet capability built into it. We talked about Mosey, Meso, clock here. If you look down at the bottom of my, let's see, and the USB port is here. If you look right here, see 6 pins?
Yeah.
That's the standard Atmel programming interface connector, 6 pins. I can't tell you which one's which, but on there is voltage, ground, clock, meso, MOSI. They're all right there. They're all right there. So these wires, they come out here and they come down here like this.
They're parallel. They're not a different set of them.
Yes. Now this is where this kind of thing becomes important when I talk about I/O
Interesting.
standards and closing and opening transactions, because there's an Ethernet shield, and the Ethernet shield talks via SPI. So now
If you don't close your transactions, you won't be getting much Ethernet.
well, you might be getting Ethernet, but you might not be able to talk to a GPIO expander or anything else that's SPI. Or if you're doing Ethernet to RS-232, you're not going to be able to make the RS-232 work. I mean, that one was a specific one. When I was looking at the SPI stuff on this, it says, if you don't end a transaction, you're not going to be able to use 232. Guaranteed. So, I'm going to take this card like this, and I'm going to flip it. This is going to be the Ethernet card, and it's got the 6 pins here. Right, so you would take it and stick it on that way. So I'm just going to kind of flop it down. Trying to remember. I think the Ethernet port is here. So we're going to see through the card. Ethernet port is there, and then it has a PHY. Actually, PHY might be built into that. We'll break it down into pieces. There's a PHY, P, H, Y, and then there's the plug, the actual port, and there's power stuff on here, power supplies, and there's some sort of a SPI to that thing. I don't have one here in front of me to look at. And so these pins basically go like that, and you bring power in on it. And there's 2 different versions of the Ethernet shield for Uno. One is the base Ethernet, and one is the PoE, Power over Ethernet. Power over Ethernet has a card that lays right there on its edge, and it is tall enough that you can't stack another shield on top of it. Or you can, but it's not good.
Some higher headers.
Well, I bought a PoE because I bought one of the PoE ones, because with the PoE
You can power the whole
you
thing.
can power the whole thing over that over a PoE switch if you've got one, and I do. And then I figured out, well, I can't stack all this shit on here, and so that kind of defeats the purpose. So, darn it. I'm sure there's some other game I could play where I make a power supply card that takes the PoE and does stuff with it. But I've read up on PoE, and PoE is a really tricky, tricky protocol type thingy going on. So, let's talk about layers.
The OSI?
Sort of. You have your signal layer. This is I'll call this your channel. We'll call this your channel layer. Signal. And then you have your physical layer. And this is going to be a really simple one. And then you have your application layer. that is the core, simplest version of any computer, any communications system, anything. Especially signal layer, we're talking comms of some sort. And now, the signal layer, your channel layer, can be physical. It can be a wire. But the physical layer is the thing that takes the application layer and turns it into something that can be transmitted across. So if we look at RS-232, there's this is the phi, P-H-Y, not the phi, even though it probably should be a phi. We call it the phi. The physical layer has the stuff to convert bits into whatever that channel is. So on an RS-232, you've got the baud rate generators, and you've got, if it's honest to God RS-232, greater magnitude than -3 volts and greater magnitude than +3 volts, right? Remember we talked about RS-232, true compliant signaling is like +10, more than +5, more than +3. I think it's more than +3 up to 12 volts and greater magnitude than -5 all the way down to -12 volts, I think. And the reason for that isolation is noise. So you can have however many volts of noise be in there and not corrupt your signal. And that's a lot of noise. So in the case of Ethernet, you've got a cable coming out with four
wires.
twisted pairs. 4 twisted pairs, 8 wires,
Well, yeah, only 2 are used,
depending.
unless you got power.
Power over Ethernet uses 2.
Yeah.
Your signal uses 2, and if you're doing gigabit, it uses 2 pairs, I think, or one of maybe the 10G.
10G maybe. Haven't done any 10G, but gig is still 2 pairs.
Still 2.
Yeah.
All right. Now, what's going across those wires is not on, off, on, off, on, off. It's RF encoding that. It's I guess maybe at 10 megabit it was on, off, maybe. When you get to 100 megabit, I think they started doing FM. And I think when they went to gigabit, they started doing Qpsk, where you're shifting phase and frequency and amplitude. And the way this works is, we talked about this before a little bit, I'm sending a signal down. If I'm sending binary, how do I do this? If I'm sending binary, I say if I get 5 volts, that's a 1. And if I get 0 volts, or in the case of RS-232, let's call it -5 volts, that's a 0. And actually in RS-232 it's flipped. A negative voltage is a 1 and a... What's that?
I think we can steal some Schultz's markers.
New markers?
Yeah,
It's starting to get dim, isn't it?
He would notice, right?
So, high voltage equals 1, a low voltage
He
equals
sounds
0.
like the kind that would mind.
Sorry.
That's binary signaling, on, off. It's a form of amplitude modulation. Amplitude shift keying, on, off,
AM
on,
radio.
off.
Amplitude modulation.
It's a form of.
Yes.
This is called ASK.
Yeah.
Now, when you go FM, you look at it in time, it'll always be plus or minus 5, but it'll increase frequency and then it'll slow down, and then it'll increase frequency and it'll slow down. And so you might say low frequency is a 0 and high frequency is a 1, something like that, right? Now, when you go to Qpsk, quadrature phase shift keying.
You'd be able to draw this.
I can't draw it.
Do we need a 4th dimensional drawing board?
What you do is you look at it this way. And you've got phase, and you've got amplitude. And let's say you send 4 bits at the same time. I can have a high amplitude and a low amplitude. I can have, we'll use frequency because phase and frequency are sort of related. I can have a high frequency and a low frequency. So this might, the way I just described that might be called quadrature frequency shift keying, but they do phase. It'll change from being at 0 degrees immediately to 180 degrees and then back to 0 degrees. And practically from the way I look at it, yes, it did that, but that's a frequency change too. It's a very sharp, sudden frequency change. And then back to where it was, and now your phase has changed. And so what you'll do is I'll say, if I send 4 bits at one time, simple Qpsk, I can be here, 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 or here. And there's some uncertainty error in there. So when I'm sampling this, you know, I've got some jitter in my phase and my amplitude. So I create these point clouds like this. But I sent 4 bits down the pipe at one time on the physical layer. And we can get into modulation, demodulation schemes, and I can actually draw what the RF looks like. But you're punching RF down the pipe. And then you can go to, I think the next step is, I don't think they do a Qpsk. There might be a Qpsk 8, which maybe does this. So the jitter makes these things land in here, but when your hardware's gotten really good really fast, right? And so the hardware's really precise, and there might be jitter and external noise and whatever else doing this, but it's very good at saying that's in that box right there. And so you kind of look at it as a series of boxes. And as long as it lands in that box, then you know that that's what it was. And if it's on a borderline and you can't tell, then you throw an error, that there's a bit error of some sort. And so then Qpsk 16, 4x4 is a 16 box. There's I think there is a 32, and there is maybe a 64. Often what happens though is you go up higher and higher and higher, these get smaller, they sort of move in, and so you have to have better and better and better hardware to be able to discern this one from that one from the other one. So the cost goes up until Moore's law catches up, and then the cost comes back down. So the physical layer is saying this. I am making the waveform that gives me the appropriate point cloud for what it is I'm trying to transmit. And on the flip side, you've got a really fancy discriminator, very stable local oscillator that's sitting there saying, yeah, this should be here, and okay, that's there. Now, history. So I've already told you that the SPI that we learned for GPIO, hopefully, maybe not, is a stepping stone to Ethernet on an Uno, because the Ethernet card's controlled by SPI. Talked a little bit about this, fun stuff that we really don't care about, but you know, this is what I was talking about earlier today. I kind of step behind the curtain and show you what's going on, and now we'll close that curtain because you don't care. Gee, that's neat. Practical for me? No. Application layer is whatever the software is that's running on top of it. So whatever bits and flips and flops. You can even look at talking between the CPU and memory as the same thing, right? I've got something I've got a PHY that's going to talk to the memory, and then it's got the signal layer, and that is subject to noise, right? You've got other things going on in the computer. Signals can cross those tracks, create false ones and zeros on there under the right circumstances, and you've got to be able to back those all out, which is why we've got all this error correcting part of why we have all this error correcting stuff in our memories. So let's talk about in the early days of networking, before token ring.
Before token ring. Wow.
Before token ring.
For ArcNet.
Are we talking ThinNet?
We're talking
No, I think
University
that was
of
after.
Hawaii in 1962, 65, I don't remember. It was the Aloha Network.
Heard of that.
It was the Aloha Network. It was so all the different islands could talk to each other. This was the forerunner to T1.
Okay, yeah.
So I've got an island here, and an island here, and a big island here. And this is not at all representative of the way they really look, I don't know. And you got another island over here, and I can't even tell you their names. I know one's Hawaii, one's Oahu, and one's something else, and so's the others. But you've got people here, and you got people here and there, and you need to be able to talk back to these people. And laying submarine cable is really expensive, and you got to replace it and go fix it, and assholes with anchors
Figure it out.
break the cables, and then you got to go fix it or lay new cable, and kind of a pain in the butt.
Damn them for wanting their boats to stay in one place.
It's actually a real problem.
I'm sure.
Transatlantic cables, the main one of the main reasons that Africa keeps, there's like only 3 feeders into all of Africa. One comes in through South Africa, one comes in from Europe, and one comes in through the Persian Gulf. And I think there might be a 4th one that runs transatlantic over to Brazil or the US, or maybe both. What happens is fishermen go out and they drag bottom nets, and they're not supposed to, and they hit those lines and they break them, and suddenly half of Africa just lost all of its internet. Half a big chunk of China just lost all of its internet. A big chunk of Europe, they lost all their connectivity with the United States, and now they're pissed because they can't get the Google. Right? All their Google nests just quit working.
Yeah.
So, and if you get caught, you're liable to have to pay. You are liable, meaning that you get to pay for the repairs, and they're not cheap.
No. There's only a few of those boats.
And the only reason I know that is the company that I currently work for lays cable and makes the cable. And I won't say any more than that, but if somebody, you can look it up and figure it out.
They figured out how to stop the resonant frequency from submarine fiber from attracting sharks. That was an early problem.
Yeah, I heard about that. The sharks like
Sharks would go down and eat it.
Sharks eating your internet.
Yeah.
It's not just sharks. When we lay fiber optic for some other things, we actually have to put Kevlar jackets on it, because crabs, turns out, really don't like your fibers, and they want to come on and they will break a fiber just like that. I mean, a fiber is like hair, right? So
I spent a day at Secor once. It's pretty wild.
yeah. So what they came up with, they said it's a trade-off. This guy might want to have a whole lot of data he needs to send, and these guys might not have much. But what we're going to do is we're going to put a controller here, and they got a radio antenna. And so do these guys.
Like a line of sight.
It's all line of sight. And he is going to control it. And he's going to control it by saying, it's your turn to talk.
You have the contract.
Now it's your turn to talk. 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 So now we're gonna show how this works. I'm gonna point to you, and you have an opportunity to say something if you want to. But as soon as I take the stick away, you don't get to talk anymore. So
Bananas.
Fred.
that.
Jeez.
right? See how this works? You get an exact time slot. You know your time slot's coming
Beer.
up.
No.
We got beer and bananas and cheese. I'm not sure that's a good combination. I think those
Hot
four
dogs.
things work against each other. So
Yummy.
this was the Aloha Network, and everybody got a time slot. You know what it's called? You're old enough that maybe you know. Slotted Aloha. It's called slotted Aloha. T1 lines for the telephone system work the same way. Used to. We've gone away from T1s to switch networks. But what you have is a T1 could be copper or it could be fiber, but they would send multiple signals down. And one was a control signal. Okay, so now I'm going back over 20 years in my memory here, because I haven't used this but maybe once ever in 20 years. You have a control signal that goes, and you have a data line. And that might be it. And so there's a box here on the end, and the internet comes along and stuffs data into this big register, right? Let's say or the telephone company, this is a telephone company, they got a bunch of data, they were digitizing their stuff. They said, you know what? For audio, this works great. T1 line, if I remember right, was 1.4.
1.54.
1.54?
Yeah.
54 megabits per second. And if you divide that by 8, that'll tell you how many different phone calls can be going on at the same time.
That's 20. It's 24.
Is it by 24?
Yeah,
No,
it's
it wasn't.
24. It's 24 time slices.
Was it 24 time slices? Okay. So it's 24.
Or it is now. I mean, at some point it may have been less,
Eight,
but
eight sounded right. But
It's
yeah.
8 bits.
it's 8 bits. But
Yeah.
you
Plug
actually
into
get
that.
620. You get
Oh, no. Okay, I'm sorry. They said our current plain old telephone system gives you a 6 kilohertz bandwidth-ish. Maybe it was 8. So it was 8 kilohertz times 8 bits, which is 64 kilobits
yes.
per second.
And there's 12 or 24 of those on
And then
that
1.54 meg divided by that
Yeah, it's
gives
24.
you 24 then.
Yeah.
I could have 24 simultaneous phone calls going on. And one of the time slots, it shared, it round robined. Maybe it was 2 lines, maybe it might have been full duplex. So I'm sending a byte to you, at the same time you're sending a byte back to me, now I'm sending one to you, and everybody has a time slot, and it's run by this control line. This control line says, it's your turn, it's your turn, it's your turn, it's your turn, it's your turn. And as soon as you see that signal go high, you go, oh, here's 8 bits! And now it's the next guy's turn. That's how it works. Now we'll take a step into the future a little bit. Then there became it was ArcNet and Token Ring.
ArcNet, Token Ring, ThinNet,
They were all competing standards.
Yeah.
And
and then Ethernet.
I think Ethernet came out of ArcNet.
I think so. And then Ethernet was flat for a long time, and now we switch it.
I just remember having to terminate the coax so your bits didn't fall out.
Yes.
Oh,
That was
ThinNet
Thin
was
Ethernet.
oh, God.
Okay.
Thin Ethernet. 10 base T.
No,
10 base 1.
it wasn't 10 base
No.
T because 10 base
No.
T is
It's
Ethernet.
Ethernet.
Is
Yeah.
regular
So it was 10
Ethernet.
base 2 then.
10 base 2.
Yeah,
yes,
yeah,
10
10
base
base
2.
2.
Yeah,
So
I did a lot of that.
Token Ring came along. So you heard us talk. There was a couple of different not topologies. There was a couple of different signaling layers. Ethernet's a signaling layer. ThinNet was a signaling layer. ArcNet was a signaling layer. But so there's a couple of different ways you could do these things. But the actual messaging the application layer, the messaging layer, how you actually sent your message traffic, which I guess that was a layer I should have put in there, was your messaging layer, right? How are we going to talk? Token ring, you used to have your server sitting here, and you had computer 1, computer 2, to computer N, and I don't know what the maximum number was. It might have been 128, might be the maximum number. But what
I forget how many addresses
they were
there
daisy
were.
chained. Data would come in here, then it would go there, then it would come there. Blah, blah, blah,
And
blah,
they were
blah.
these big honking connectors.
They were being, the ones I used were, oh yeah, you're right, there were some that were.
The original, yeah.
The original ones, they went to
IBM
BNCs for a while.
In the end,
Yeah.
yeah.
So the server just starts spewing data. And this guy knows that, you know, his address is number 3. So he sends like a start bit. He sends like a start you know, he says, here, I'm starting my data. And he knows that he's the first one on the thing, so he gets the first n number of bytes. But he reads them and writes them at the same time. So his last one that he was supposed to get, he writes it out on the network at the same time he's getting this one in. And now this guy knows he's the second guy on the network, so he's supposed to listen to the second one. So the first one he got was this guy's output, and the second one he got was this one. And so he spits out. So now I've got
So it's like a train where each car.
I've got
is
C1
belongs to a
out.
computer.
I've got, this is C3. My first thing is C2 out, I'm sorry. C1 out, server out, right? So, yeah, it's a big train going along. So now 100 and whatever n cycles later is, the server gets his, and he gets his, right? He got the last bit in the chain, and now it just keeps going. This is a token ring. You can see that maybe that's a little bit better than slotted Aloha in that I can keep the line full all the time if there's stuff to be there. 2 downsides. If these guys are turned off, I'm wasting a lot of time doing nothing. I've got this channel that's 10 megabits wide, and I can only use, I will never go over half of it. I will never go over half of it because half of my computers are shut off. Wasted channel space. Problem number 2, that wire breaks. Everything dies. And now you're going through, which one died? I don't
like
know
Christmas
because
lights.
none of them. It is. You're like, is it this one? No. Is it this one? No. First thing I've worked on these. You go around, check all the connectors.
Yeah.
Does it work? No. Now you get your golden cable and you go hook up a little thing with a loop back. Does that work? Yeah. Okay. Now you go from plug to plug. Does it work? No. Plug to plug. Does it work? No. Plug to plug. Does it work? No. And invariably, it's like the second. Whichever way you go,
The
it's going
last
to be
one.
the second. It's going to be the second. No, not the last one.
It'll be the second.
The second
No,
one.
last one.
FYI, I was wrong. It is all four pairs for full duplex gig.
Okay. So that's token ring.
So that's shitty. So we don't use it anymore.
It's really reliable except for the cabling.
The cabling's a problem. What's good about it, okay, the downside is if this is, let's say it's 10 megabit, nice easy numbers, 10 megabit, and you've got a server plus 9 computers, so this is 9. 10 megabit over 10 computers means that nobody's ever going to get more than 1 megabit bandwidth. I get a packet in, I packet out. But I get a constant 1 megabit. I get a constant 1 megabit. Any device on the network has a constant data rate that can be pretty well much guaranteed. That's a great guarantee. That's nice. But if a wire breaks, it's a pain in the ass. And if this guy's shut off, again, if half of them are shut off, I don't suddenly jump up to 2 megabits. Now I've got 5 computers that only get 1 megabit. So my total data rate is never going to go above 5 megabits. So now that's a waste. It's a horrible waste. Now we're going to talk about Ethernet. What we currently call Ethernet. And where's the light switch for this room?
It's by the front door.
Hopefully I don't shut off the back too.
Yeah, and Rob's not here, right? Because that shuts off the light in his office too.
No,
Somebody can just jump out and say, what the hell?
No, he's had the light shut off on
This
him.
isn't fair because your computers are on and you can see the lights, see the glows. All right, close them up. That's better. Now, we're going to start saying stuff. We're going to figure out how to get things across to each other. Whenever you feel like saying something, you have something to say, you wait for the first time when there's a when there's a halt in speech, and it's your turn to talk. If 2 people talk at the same time, you stop. You do what you normally do. It's called a collision. You stop for a second and you wait. Whoever gets to, and anybody can talk at any time when it's quiet. Ready? Go. I like beer.
more beer.
Fish.
Courage and away. Little Miss Muffet sucks.
Sharks. Sharks.
Sharks. Sharks!
Where are we going now?
Sounds like a Reddit thread.
I hate puppies.
I hate cats.
You monsters.
Well, they taste good.
Love cats.
Pizza.
All right, so that's enough. Now, do you see what just happened there?
That's basically on fire at this point.
No,
Oh,
stop.
I'm on fire at this point.
Great. Podcast decides to start when I get a notification.
Yeah.
Yeah.
That's how Ethernet works.
So collisions.
It's a bunch of people sitting in a room in the dark.
Yeah.
Okay,
Bunch of puppy haters.
it is. Every computer is on its own time base. My software just told me to send a packet out on the internet. I want to get some webpage somewhere. Is anybody talking? No, that means the channel's free. I get the whole 10 megabits. I get it all. I get it now. Nobody else is using it. It's mine, damn it. I don't care what you think about it. I'm going to be here and I'm going to be loud, but it's only going to be 1 packet. So that 1 packet in standard Ethernet is 128 bits, I think, or maybe it's 64 bits. It's either 64 bits or 128 bits of header that says this is where I want this packet to go, this is the checksum that's in it, this is how big it's going to be, and then the standard Ethernet packet I think is only I think the whole thing's 512 bits.
1522, I think.
That's a
Oh, no,
big frame.
1518.
Large frame.
1518.
That's a large frame, I think. I think it was originally 512 bits. The first 128 were, this is where I want you to, this is where I came from, this is where I'm going, this is my time to live, this is some other things, and then the rest, the other 384 bits, or whatever the number is that equals to, was the actual data. And so now I'm sending out 512 bits, and I stop. And I wait some random amount of time, because maybe you want to send a packet out, or maybe you do, or you do. Nobody sending anything? I'll send it again. I'll send it again. It's quiet, I'll keep sending. It's quiet, I'll keep sending. It's quiet, and somehow we both decide to start sending at the same time. It happens. Statistically, it's going to happen. Bang! And I'm hearing, right, at the same time that I'm talking, and that's not what I said. Shit. Stop. And he does the same thing. Wait a second.
Wait.
And now I'll talk again. And while he and I are saying, crap, wait, maybe you pipe up and say, oh, I like beer too. Your packet gets in on the traffic, right? You just got a whole 10 megabits when you needed it. Or pretty close to when you needed it. I needed it. He needed it. When we start talking three-way, it's going to be very near a third of the bandwidth for each of us, right? See how that works? I had 10 megabits bandwidth. He starts talking, I wait, I let him go. But now I talk, now he talks. Now, all 3 of us are talking We're figuring out the time slice ourselves, how to fit things in, and we're very near the full capacity of the network. And then when I'm done, and I step off the network, and somebody else can use up capacity that I don't need. If it's 10 megabit and there's 10 people talking, maybe I only get 9 megabits or 8 megabits out of it because collisions and I'm waiting my turn and you're waiting your turn and these little random spaces in between. But I'm going to be making much better utilization of the network than I am on a token ring. And if you get laryngitis or go to sleep or get turned off, whatever,
We get your bandwidth.
we get your bandwidth. Right? Oh, I didn't just lose a bunch of bandwidth because that guy was that half was turned off. You know, half the world's asleep at any given time, right? All of these guys are awake are going to use all the bandwidth we can, and now all these guys are awake are going to use all the bandwidth they can. That's how Ethernet works.
Okay.
That's how Ethernet works. At the physical layer. And the PHY. The PHY on a Ethernet is this Qpsk type stuff going on, and it's some magnetics. There's like little inductors in there that do transforms. They are not directly connected in. They're connected in through a magnetic little transformers, which is one of the things
That's the part that you blow up when you get a spike. When you get a
yeah,
lightning strike.
usually, yeah. Actually, no, not the magnetic. If it's a spike, it comes through and blows something else up behind it. But the magnetics are usually pretty good. But the Ethernet cards often have some sort of fusing in them so that if something hits them, it doesn't go all the way
All the
through
way
it.
back through.
But anymore, it doesn't matter because it's integrated onto a motherboard, so they probably got rid of that crap because,
It's toast anyway.
yeah, it just toasted the whole machine. I mean, I can't talk to anything, so what good? I guess this has an Ethernet port and a Wi-Fi, so
Yeah.
it might still be on there. I could go to Wi-Fi. That's how Ethernet works. Now, it's been a long time since I've done much of this. I used to be, you're going to be all over this, I think, from the sounds of it. I pretended to be a network administrator once for a few years, and I haven't done it in a long time.
I pretend to be a network administrator.
Okay, so at least two of you are going to be all over this. My computer, this gets weird, has an Ethernet card. Sitting attached to its motherboard. And then I have CPU and software.
I thought for a minute you were drawing the internet on the wrong side.
So in the very beginning, this is called a star topology. Ethernet has a standard. It says that you can't be more than 500 meters, I think, and that's because of timing. If you're too far away, when you start to talk, by the time somebody else starts to talk and can realize that you've already talked and you have the collision, it kills the whole network. So there's a time, distance is time, right? Speed of light, near speed of light for signaling. So the Ethernet standard says you can't be any more than this far away. It also says you can't have any more hops than some number between two ends. There's a few other things. But once you get like out of your house and into the telco stuff, most of that goes away because they've got fiber optic links that are bandwidths this wide and hundreds of miles apart, and they're dedicated links that don't have to worry about this kind of stuff.
Yeah, those limits are a lot of those are electrical limits, not the protocol itself.
Right. So, originally, the internet was new. When you were networking small computers, you weren't connecting to anything but the other computers may be in that room, in that building, not very far away, never more than 256, or very rarely more than 256 of them. You still had a mainframe that did all your main stuff, either with punched cards or WISE terminals or something like that, which talked by RS-232, by the way. And this was a hub. A hub, data comes in, it's echoed out everywhere, it goes everywhere, all the time. I make a noise, I pollute the whole network. All 256 devices have to listen to me.
Especially the ones in promiscuous.
Especially the ones in promiscuous mode. I forgot all about that. That's the guy out there with Wireshark or whatever.
Hey, it's on here. Use it every day.
So let's imagine that we've got 256 computers. Actually, 200, not.
I forget what the number is because it's been irrelevant for so long.
Well, no. There's 0000 there's like some reserved numbers, so it's more like 250 or 228. I think it's 250 real addresses. How do I talk to each other? Right? I'm going to take a piece of software and I'm going to put it on a computer, and I want it to be able to talk over this GWiz interface. How do I know that it's talking to me? Part 1.
MAC address.
This guy has a MAC address. And I honestly don't know what MAC stands for. I think
Machine address.
Yeah, something.
Code. Machine
I
address.
think
something.
that's right. And it used to be, was it 5 octets? Or was it 6 octets?
It
Is it like 8 now?
It's
May have been 8.
6. I think it was 6 octets.
Because I know the first like 3 or 4 or whatever, like
Company.
vendor.
The first 3 are the company.
3, okay.
The organizational unique identifier, and then the last 3 are the network interface controller specific.
So yeah, if you guys have ever seen a MAC address on a
And now
network card or
there's
something, you can tell
the
who made it
8-bit.
by the first 3.
The last 2 are unicast versus multicast, or globally unique enforced, or locally administrated. In the newer, I guess, world.
So that says these are sysadmin controlled.
Yeah.
And the first 3,
First 3 are the company, basically the
So
manufacturer.
3Com.
So 3Com, yep. 3Com, Cisco, whatever.
3Com, Cisco, a million different vendors.
And the last 3 are supposed to make that unique within that vendor space.
So that's the unique ID.
And every now and then you'll have a situation where you'll have like a cable provider or something, and they'll provide you with a router and say that's the only router you're allowed to use, but maybe you want to use your own router, and some routers let you do MAC spoofing, so you can set your MAC address
Some
to
cards,
the allowed one.
every manufacturer has a set of MAC addresses. They only have this many, so that's 8, 16, 24. 2 to the 24th bits is a million. 2 million. What's 2 to the 24th? Mister, I got a computer right
I was
here.
thinking it was right there. Oh shit!
That's not something I can do easily on my phone.
Alexa, what is 2 to the 24th power?
Sorry, I don't know that one.
She might not have heard me completely, but she might also not be good at math.
Scientific.
Alexa, what is 2 raised to the 24th power?
2 to the power of 24 is 16,777,000.
So 16 million.
16 meg.
16.
That's 16 million addresses here.
That's a lot.
Are you sure it wasn't just the first two?
No, it's 3. Now, I mean, I wouldn't be
I don't
surprised
think
if
there's ever been that many.
I wouldn't be surprised if, like, you're given the first 2 are your company, and then you get to specify the other, the other 2
Well, but these
within that class.
These two, you were saying, were region and whatever else. So 3Com's got a factory in Denver, a factory in Los Alamos, they've got a factory in Berlin, they've got a factory in China, and they've got a factory in Taiwan, right?
You've got too many.
Well, these were the last 2. You were saying it added on that made it 8.
Yeah.
It was originally 1, 2, 3, 4, 5, 6, 7, 8.
No, it was originally 6, and the last 2 make it 8.
Ah, I misunderstood.
Yeah,
All right.
sorry. That's where we were
There we
off. Yeah.
Okay, there we go. So, so there's like 255 possible manufacturers, or maybe 1,024 possible manufacturers, and each one of them has 255 locations that they can say. So if you get a card from 3Com, it's got this code here that says 3Com, and it came from this particular factory over there, and so that's reserved. It's only going to be, even though there's 24, even though there's 16 million possible combinations there ain't 16 million different Ethernet factories and providers around. So that gets horribly underused. I'm surprised they haven't changed that, but they had to maintain backwards compatibility.
Well, they just give you multiple if you exceed your 16 million.
I don't know anybody in Chicago, so I'm gonna let that go to.
If you answer it, you could.
I have fun with telemarketers
Today is
sometimes.
a day of firsts, Tom.
I have fun with telemarketers sometimes, and I'm not sure we want that on the table. I've had them hang up on me.
I usually try to get them to hang up on me.
I like asking them what they're wearing in my sexiest possible voice.
Wow.
Yeah, you would.
I don't care what. I don't care if it's a male or female. What are you wearing? What? What are you wearing? Click. My job here is done. So this big long number is how, when you send something out the door, it knows who to talk to. How easy can you remember 1, 2, 3, 4, 5, 6, 7, 8? 8 times 8 is 64. You think you can remember a 64-bit number? I can't, because that can go up to really big numbers. That's terabytes. That's not easy to remember. And the truth is, when you get down to this part, that only a certain amount are allowed to change, there's more than that many devices in the world, right? And so when you say that this is limited to some small number of manufacturers, and this is the only thing that you do your addressing with, that repeats. Likely there's 10 of those in the world. So when you want to talk to your internal network, that's fine, because actually I did get 2 different cards that had the same number on them once. Some of the cards are reprogrammable. You could go in and
Well,
you can't have that one.
That usually happened because they were offshore.
No, I had 3Coms.
You sure they were really 3Coms?
Yes, they were. Really
It wasn't
3Com, naughty 3Com.
They weren't 30Ms.
No, they were 3Coms.
3CMs.
They were 3Com.
Can't tell.
They were 3Com Etherlink 3s. With all the manufacturer goodies and everything. Straight from 3Com.
Okay.
So yes, I've actually had it happen personally one time on a small network where,
Yeah.
it's like, dang. And I also had one card that would occasionally, I had one card that every now and then, it must have been off by like 1 bit from another card. Because it would come up and it would read it's 1 bit different, and then I'd have 2 of the same on the same network. And you go reboot the machine and it would come up and everybody would be happy.
Yeah. Not fun.
What the heck? So yeah, there are utilities out there that will let you write your MAC address, and that's more and more common. So now when I talk, I say, oh, I want to talk to computer such and such, but when I put this card in, I don't know what that MAC address is. I don't have any reason to know what that MAC address is. Only this guy and whoever he's talking to needs to know that MAC address. So I create Internet Protocol, right? And so the Internet Protocol v4 is 4 octets of XX, YY, ZZ, AA, ... And there are several of those that are non-routable.
192.168.0.0.10.0.0.0 and 22.24.0.0.0.
And Microsoft has a like 269 dot something or whatever. It was a, if you're not smart enough to set up your own network, we're going to default to this, so everything on your network has an IP address.
So we used to have hubs, and everybody would talk to everybody inside of here, and then you had a router. We would all get assigned an address, and they would change just these bottom numbers, right? If you look at your work PCs inside on the solid network, and you go look at your friends and your neighbors and that guy you hate and your own, you're going to see 4 IP addresses that the only thing changes is this one. These last
4 octets, and the only thing that changes is the last octet.
is this last octet that changes. And that octet, it can be a number between 0 and 255.
Well, 1 and 254.
Yeah,
254 is 255 is
No,
broadcast.
255
and
is
0 is
broad-
network.
Okay, again, reserved addresses. It can be anything from 0 to 255,
Yeah.
but there are reserved
And
addresses.
specifically, you're talking about subnet mask 255.255.250.
Yes.
We'll get there. So,
Slash notation or dot notation?
noise comes into the hub, and it goes everywhere. If I want to talk,
Slash 24.
my header to my Ethernet packet says, I'm this guy, and I want to talk to that guy. Everybody else on the network ignores him, except for that guy. Oh, that was a message for me. And he can do with it whatever he wants. He might do an acknowledge, he might not do an acknowledge, he might go off and do whatever.
We're still in the hub world.
We're still in the hub world.
Yep.
We're still in the hub world. And now it's not actually this that's doing it, it's the MAC addresses. They're actually only listening to the MAC. But then there's this extra layer in the software layer here, the application layer, that's doing this. So it's not the hardware per se. This MAC is built into the hardware, and it masks everything that comes in. It gets in this great big chunk of stuff, and it says, that was for me. And then it passes all the rest, it passes it all along. And then there's some translation here that goes between IP address and this. So we're back in the hub world, back in the old days. I came out, I hit my router, pretty much might broadcast everything that's going across the inside, right? And somewhere, or even if I just say 1 and it comes across the router and goes out, I could have the same MAC address somewhere. So this is a second layer that says, oh, I got this MAC address. Should I the card says, I'm going to listen to this, but then at the software application layer it says, oh, but that's not me. Throw this away on the trash pile. Now I get over the problem that there's more than 2 million computers in the world. Or 24 million computers in the world. What was it? 16 million? What was
16 million.
it? 16 million computers in the world. So now I can play another game
All
yet.
the way in the back on the left.
With my net mask, I can say that half of my computers are on 255, 255, 255, 128, and the other half are
No,
on.
that makes two halves. It's just the IP space then splits in half. The
Is that
last
how-
octet is then split in half. So
Okay.
it's 0 to 127 and 128 to 255.
There you go. Or you, so now I've got a 200 and some odd computers, half of which they don't listen to anything that's on the other half. And now you can have a computer over here acting as a router that's one wire, or it could be dual homed with two wires. Right? That's what we usually do, is we dual home it, so it has two Ethernet cards. And this one has the 128 net mask and 0 through
0 through 127
127.
and 128.
And this one has, is it the 0 or is it 129 net mask?
120. No, it's not mask. It's just IPs.
No, the mask is different on the two.
No. The mask is the same on that last octet. You can only divide it once, if you're using 128. So it's 129 to 255. And you can't use 0 and 127, and you can't use 128 and 255 for actual machines, because they become the network and the.
I thought there was a different mask on each one.
No. You can have, if you break it down smaller so it's not two, you can have different subnets within the same class C.
Yeah.
But if you do a a 128, which is a /25, half of a class C, it's the same mask on both sides and just a different network number and broadcast number.
Right.
It's
Guaranteed,
been
yes.
it has been 20 years.
Gateway number?
Yeah.
Yeah.
Gateway is it can be anything, any IP.
the gateway is
network
usually-
number is locked.
The
okay.
gateway is usually which
The
card.
IP address of the router, but it can be any IP address out of that range.
But if you've got your routers dual homed, it can have two gateways.
Yes.
Well,
The machines on each LAN segment or each subnet only have
Well,
a gateway
we'll-
out. The
we'll do
gateway
it.
can have multiple gateways, but it has to be out of the same subnet.
We'll do it this way. So this is the internet. That's an N, not an M. He could be a gateway. This half would say he's their gateway.
Yep, correct.
This half would say he's their gateway, and he would say this is my gateway.
Yeah, the next router out.
The next router out. So
correct.
All three of these could be a gateway. They just be different
Yes.
people's
The
gateways.
It's the gateway for your next hop.
We're going a lot further into this than you're going to actually need, but now we don't. I actually still have a hub at home.
Yeah, I've held on to one or two.
It's actually
Sometimes-
running.
Yeah, well, sometimes it's fun to use for.
Well, I've got 10 computers.
Dry nice.
I've got 6 computers wired to the hub. So now we don't use hubs. We use switches. And a switch and we don't really use routers, we use switches.
Within
we
a
use
network,
smart switches.
within a network, you don't really use routers. So most corporations, unless they're really big, wouldn't have a router between multiple computers unless it was for security purposes.
Now we have a switch. And there used to be a distinction between a switch and a smart switch, which means something different than it does now.
Yeah.
So I've got this computer and this computer and this computer and this computer. And each one of these connections now has a MAC address. So now this switch, if it's a 16-port switch, it has 16 MAC addresses, and you can now really start to see how those MAC addresses get used up fast, right? But now this machine, his MAC only talks to that MAC. And the switch knows that this is the MAC that's attached to it, because the first time you plug them in, they start to talk to do some negotiation. He says, I know who you are. You're on this port. If I ever hear anything that's supposed to go to you on any of the other ports, I'm just going to take it and send it straight there. And so he says, I want to talk to this computer, and bam, he just switches it. He switches it, just like a train track switch. Bang. And he sets up a connection between those two computers. And I think the very, very first generation switch would only do that. It would kind of tell these guys, shut up while these two guys talk. That was like Rev 0.01. Then the very first real generation of switch could do this. These two can talk and use up the full 10 megabit bandwidth, and these two can talk and use up the full 10 megabit bandwidth. And now I've just not exactly doubled the capacity of my network, but I've done a lot for it. But
The big thing is you've totally changed the collision factor.
yeah. Now, if this guy, but you've added an overhead. If this guy now says, I don't want to talk to this guy, I want to send a packet out to that guy, now you've got to take the time to break the connection and make the connection and break the connection. Right? So now there's a little hiccup in the network. Oh, you want to, but he stores that packet for a second while he does all this work. So that slows it down. But a really good smart switch can have, if it's got 16 ports, it can have 16 computers, which means it can have 8 simultaneous 10 megabit connections running on it. Or today, gigabit or gigi or whatever, but they can all be going at the same time. And so now you can really utilize the bandwidth, right? Where before, if I had a 10 megabit network with 10 computers on it, I was going to peak out at 10 megabit, and usually I was going to be somewhere around 2 maybe. Now, when 2 specific computers are talking, they get all the bandwidth. Big advance. The router out here, he does sort of the same thing. He says, if I see anything that's for XXYYZZ, it doesn't go past. I'm not going to pollute the rest of the world with my data. I'm going to keep it over here. You guys yammer away. I'm going to close the door so nobody else can hear you. Now he says, hey, I want to go talk to Google. Oh, that's not on my network. And he's going to say, he's going to look in his own list, a modern router. He's going to look in his own list. And he's going to say, I don't know who Google is. And now he's going to go out and he's going to ask the next tier up, which is feeding a bunch of these routers. And he's going to say, do you know who Google is? And he's going to say, and we use google.com. I can remember google.com and yelp.com and ipicicles.com. I can't remember 10.10.1.3. And in fact, when I hit google.com, I'm actually hitting a server farm that's probably 1,000 addresses. And depending on where in the world I am, it's going to route me to this data center, and it's going to look for the machine that's least busy, and it's going to say, you handle this request. And so when I go to google.com and set in a query, I'm actually talking to like over 1,000 different machines around the world. And it's going to smart route me based on a couple of different things. You should go here, you should go here, based on real-time metrics. Go to this guy, he can handle your request better. No, you asked a question in Chinese, I'm going to send you over here to this server in Albania. And you asked this question in English, so I'm going to send you to this server over here in Russia. And just to be apropos with politics at the time. And this is where we were talking about non-routable addresses. So inside your home, if you look at your own IP address, it's probably 192 is the AA. And often you'll see that your telco or whoever it is that's supplying your Ethernet connection is 10 dot something. No router will allow those addresses to go across. I can do everything I want. Actually, it's 192.168. And then these
Are available.
1,000 some odd, these 16 bits, 32K I think, or 8K.
A whole lot.
those addresses will never cross that boundary. So when you're on your internal network and you've got 6 machines and they're set up and they're talking, nothing they say will ever go across that router. The way you get across that router is smart, and it's a bridge.
NAT,
It uses,
network address translation.
or there's another version. NAT's what's usually used, but there's something
That's
else.
the only.
I think there's a port translation type.
Well, that's a subset of NAT. Yeah.
So network address translation is, you have what's called ports. So this is important. Important. When I talk to you, you might have a web server, and you might have a telnet server,
20.
and you might have an FTP server,
23.
and you might have a Skype server.
Telnet's 23, FTP's 21, 22.
Add them backwards.
So I'm going to say I want to talk to google.com. Shit, what's HTTP?
HTTP is port 80.
Port 80. When you use Netscape, Chrome, Internet Explorer to get a different browser, something like that, when you say I want to go to google.com, you're opening an HTTP connection, Hypertext Transfer Protocol, which goes to port 80. So it goes out to google.com, port 80, and says, I want to talk to you. Now, port 80 could be getting a request from anybody in the world. So what he does is he says, okay, he internally assigns a port that's higher than 1,000, is it higher than 1024?
No, he doesn't do that.
Used to.
No, you're coming from a random IP.
I'm
port.
coming from a random IP address and a random port, and I hit port 80, and he's not going to talk back to me on port 80.
Yeah.
He's going to come over here and he's going to
He
assign
can.
a, he can, but he
can.
probably won't. He's going to assign a port that's above 1024 because he can go from 1024 to 32,000, and he's going to say, you expect to talk to this port now. And I'm dedicating this port is talking to you all the time until we kill connection. And so now he can handle up to 32,000 connections and not get them.
Some protocols work that way. HTTP and HTTPS almost 100% stays on port 80 and port 443.
I do that.
Almost,
All right.
yeah, almost exclusively.
And if you look, there are certain things that use this port. You know, if you're not trying to get HTTP, don't go to port 80. You know, if you are using a web browser, it is going to default go to port 80. Even though you put in google.com, you could say google.com:80, and that's the exact same thing. If you said google.com:24 is telnet?
23.
23, if there was a telnet server there, it'd pop up a telnet window maybe. And then you could be working at the commands, at the command interface, serial interface type stuff. Now, why does this matter for you? Because we're going to talk about the Ethernet card. There are Ethernet libraries. There's a couple of different Ethernet cards out there, but for the Uno or for whatever device you want to use, the Ethernet card itself is dumb. It has a MAC address. So we talked about the physical layer and the signal layer. It's going to handle the signal layer for you. It is the physical layer. And now you're going to have to set up another physical signal layer. And that will be the SPI. And there's two ways to do this. You can write all your own code to talk to the SPI and talk to the danged Ethernet card. Or you can use the Ethernet library. And the Ethernet library will take over the SPI port, and it will go out and talk to the Ethernet Shield, and it will do the setups. But you need to know how you're going to set it up. So you've got your IP address that you're going to have to put your IP address into. You're going to have your net mask, which you're going to have to put that into. If the router that it's connecting to supports DHCP, which is Dynamic Host Control Protocol, then you're regular computer will come up and send out a special packet that says, hey, I need an IP address. And your router will say, I allow you to be on my network. I trust your Mac, you're somebody I trust or know or whatever. Here's your IP address. And a lot of them will say, I don't know who you are, but I'll give you an IP address anyway. Network security is a thing. And it's a thing you should be worried about if you're doing anything on the internet. Russian hackers aside, WikiLeaks will get into there and tell people what color underwear you wear, if they care. You have to manage all that from the software within the Arduino and figure out how and when you're going to deal with data going both ways. There are a lot of FAQs and tutorials and code snippets out there that you can look at. I'm not going to ask that any of you go buy an Uno and then buy an Ethernet Shield, because the Ethernet Shield's more than the dang Uno is. They're like 30 to 40 bucks. I've bought a couple of them. I have written code for them in the past. I'll try to write some up or pull some of my own. But where this gets interesting and where you might really want to, the reason you want to do Ethernet code for your Arduino is multiple. The fancy word for it now is called the Internet of Things, right? I want to do a weather station, right? I want to have a little black box that sits outside and measures the temperature and measures the humidity and tells me if the sun's out or not, so I can maybe clouds, is it bright or not bright, and I can be smart and figure time of day, and I don't know what else, listen for cats. And I can have this little guy just sitting up in the corner of my porch, right? And it can be talking over Ethernet or Wi-Fi if it's a Wi-Fi card, because it's basically the same. Wi-Fi is just over the air instead of over a wire. And then inside, it hits my network and comes in, and I can turn on my computer and pop up a, hey, what's going on out there? Oh, it's 37 degrees, it's 26% relative humidity, it's cloudy, and the cat's pissed. Right? The cat's out here yowling. Go feed the cat, or let the cat in, or something like that. Or maybe you also put a light on it, big honking bright LED of some sort, and say, okay, let's turn the light on. When the light goes below a certain level, I'm going to turn this light on, or I can turn it on manually from here. I can hook the doorbell into it. I can have this one little node that does a whole lot of stuff, and all I got to do is get power to it. And now I don't care where I am in the world. If I know how to get to that, I can see what the temperature, the humidity, how angry my cats are, is the light on. But remember security, because if you can do it, anybody can. And that's why I've rambled for the last hour and a half almost on Ethernet, so you understand what it does, how it works behind the curtains, and now why it matters on you. And this is, and I wanted to go into that because that's a lot more interesting than this is what you got to do than this last 5 or 10 minutes. So, or at least I think it is. And so you guys, this is your first time on the class, you understand how I go off onto a rambling rant every now and then, some tangent, and why you might not want to sit down and watch 8 other classes worth. The Ethernet shields carry all the pins through, but you'll need to understand that the MOSI, MISO, and clock pins won't be able to be used. And I want to say there's 1 or 2, I think there's an interrupt pin, and there might be another pin that can't be used. So when you throw the Ethernet shield on, you lose 1, 2, 3, at least 4 or 5 of your IOs when you throw Ethernet on. Important to know.
So you can't, with Ethernet, you can't share the MISO ports. It's not locked to an address.
I don't know.
Okay.
I've never tried. I don't know. Google.
Yeah.
Can I use an Ethernet Shield and a I/O expander at the same time or something
I
like
thought
that?
you would just know that.
No, I don't know that. The other thing that gets interesting is I did this for something. If there's a couple of sites where you can do your own Internet of Things.
Yeah, Blink is one of them.
Oh, Blink, that's one I didn't know about. Is that blink.com?
I think so. The app is called Blink on your iPhone. I've got my weather station, which isn't working at the moment.
It's nice to know. There's blink.com, there's io.adafruit.
Yep.
Yeah.
I used Blink because that was example code that was part of the project I was building.
And there's,
Yep.
is that they.com?
Is that what? .com? I think so.
Oh yeah, I use that. I
If,
started using that.
if,
If then that.
If then that, yeah.
if this,
If
then that.
Yeah, it's with 3 T's.
Is it 3 T's? If this then that.com. All of those, Adafruits is free. I don't know about Blink. If this then that, I think has
So
like 2 levels. One's a subscriber level,
Yeah.
they let you do stuff, and one barely doesn't let you do
Yeah.
anything at all. And there's
The
a
free level,
I think-
lets you do a lot.
the real question in a lot of what one to use, I would say, unless you want to get really low level like this guy, is who has a library that for whatever platform
Yeah.
you're on. Which for the traditional Uno is probably everybody. But when
Adafruit
you-
has a good library.
Yeah, when you get to some of the smaller little devices, which I think is the cheapest way to mess with Internet of Things stuff, the like tinier ones, because they have Wi-Fi built on, which is cheaper than
Like
that.
SV86s.
Yeah, than that and a Shield.
So
Yeah.
one more sort of related, if you ever need to just collect and graph a lot of data, initial state, they'll connect to like Smart Things and some other stuff, and you just throw gobs of data into them, and they just go, okay, here you go. Kind of interesting, but they don't control out from there like the other ones do.
Right. So so the Adafruit one, it was in beta. I don't know where it is now. I haven't used it in a while.
They're still promoting it, so
Yeah,
You could set up
and I'm sure they still will.
variables there that track, so you could have like a button that turns on and turns off based on what a switch is doing. You could have controls where you could turn an LED on and off, for instance. You could do graphs. I was actually sending temperature back and watching the graph on a once a minute type basis.
Oh, and for business, Zapier is the business version of if then that.
Zap.
Zapier. They are much more
IER.
IER. Yeah, they are much more business oriented. So it's a lot of Microsoft Office online integrations, things like that. You know.
There's also some people that do stuff. I think they'll charge. They will pull back stuff like from your HVAC, your heating and air conditioning, and your elevators and things like this, and they'll do process monitoring for you. And they'll be able to tell you, or you'll be able to look and say, "Wow, that air conditioning unit over there is running a lot longer than it normally does, or a lot more than all the rest of them are." So that tells you either there's something wrong with the air conditioning unit, or maybe there's an open window, or something like
Right.
that.
Our friend Alan apparently is working for a company now that one of their clients is the Empire State Building, and it's something with data collection for the HVAC systems and doing smart analysis of how to heat and cool giant buildings.
Some of them are actually, one of the places I was reading about, they'll put vibrometers on all the motors. And they'll not only say the motor's running and the motor's not running, but they can start to look at it and say the motor's running rough. So there's a problem with the motor. Or they'll look at the power factors. And they're really neat because they'll put it all on the main switch, not on the individual motors. And I'll start looking at the current draws and it'll learn, oh, I don't know what's on, but something's on right now and it's doing this, and now something's doing that, and now something's doing this. And you can sit there as the user and you can say, well, my lights just came on, my lights just turned off, and the AI on the back end says, oh, this is your lights, this is your heat pump, this is the blower motor, this is the water heater, and now I know when it's on it looks like this and this and this and this, and hey, that doesn't look like it usually does anymore.
I'm doing this in one of my facilities right now.
Right, and now you on the maintenance end, you have the choice of, blow it off and let it die before I go fix it because I'm a cheap slumlord, or I've got $1 million computer farm sitting here and that's getting ready to go bad. I need to go fix that now, right? I mean, take your pick. Not that the data farm's not kind of a slumlord, but and I guess that's really about it. So tonight, let's see. If you have an Ethernet card, I'm going to invite you to go look up code, write some Ethernet code for it.
I'll bring in my weather station working.
Yeah. But yeah, like I said, I want to get to a project eventually where we have some fun with something. I think next time... Come on. She went to sleep. Maybe I never woke it up whenever I opened the lid back up earlier. I think next time I was thinking I was going to talk about the LCD shields.
Yeah, it might be fun to play with sometimes, especially the touchscreen ones.
Yeah, I don't have a touchscreen one. I've got just one of the plain LCDs. It's got like 4 buttons and a reset button and a 2-line 16-character, 2 16 lines.
I've got one.
2 16-character lines.
I've got an
LCD.
Adafruit one for a feather.
Yeah.
I haven't played with it yet.
I actually did a thing as a learning experience, and I think it actually made it to, yeah, it did. It made it to EE Times, I think. I wrote lab Windows software to control it, so I had what looked like it here on the computer, and there it was over there, and I could press this button and an LED would come on, and I could had like little dials that were showing me what the ADCs were doing on it, and I had the LED or the LCD screen, and I could type something in there, and it would come out on the LCD, and I could adjust the brightness of the LCD, and it would change the brightness on the LCD. And,
Cool.
that was a fun little learning experience. Personally, oh, what the hell?
Do you guys
Setting
want a quick tour of the rest of the space?
Yeah, I'll shut this down.
Since you only saw the first 10 feet.